Okay, welcome back to Real Analysis. Continuing our work in section 7.6, we're going to pluck off another major theorem from calculus. This time we're going to be looking at the mean value theorem. So this is in the second subsection of 7.6. So I've got kind of a visual statement of the mean value theorem here. We can kind of walk through the hypothesis. It's similar setup to Rolle's theorem. It's just that we're going to drop the requirement that the function values at the endpoints of our closed interval have to be the same. Okay, so if we look at this picture while we're kind of walking through this stuff, we've got a couple of numbers, A and B in the real line. We'll suppose A is less than B. Once again, the hypothesis are we've got a function defined on that closed interval. And the same two kind of fundamental hypothesis as Rolle's theorem. That the function's continuous on the closed interval from A to B, differentiable on the interior of that interval. So you can see in my picture up here, I've got this function f drawn. It's labeled there on the right. The font is kind of small, but that black curve, it looks like the function is defined for values outside of the interval from A to B, but in particular, between A and B, the function looks like it's continuous and differentiable. Okay, so what Rolle's theorem would say is if the value of the function was equal at the two endpoints, then the derivative would have to be zero somewhere. Here we're dropping that condition. So you can see in this picture here that f of a, the y coordinate at the point that I'm kind of highlighting in blue there, is not the same as f of b. Those two numbers are not equal. All right. But what the mean value theorem says is that there is some value of c, there is some input in the interior of this interval that will make the derivative of f equal to this so-called secant slope. Okay, so I've got that secant slope drawn there, the secant line rather is drawn in red. So this number f of b minus f of a over b minus a, it's nothing more than the slope of that line that I've labeled L there. All right. So what the mean value theorem is saying is that somewhere on the interval, the interior of the interval, the derivative will take on the value of this secant slope. Like we said, we're not kind of emphasizing it here, but in calculus, you learned that derivatives kind of represent instantaneous rates of change. A lot of times this secant slope will be called the average rate of change. So this mean value theorem is saying that the instantaneous rate of change is equal to the average rate of change at least once. Average, another word in mathematics for average is the mean, the arithmetic mean, hence the name of the theorem. The mean value theorem is saying that the mean value of the function, the average rate of change, is assumed instantaneously at least once. Once again, I say at least once because as you can see in my picture here, the font and typesetting aren't that great, but there's two values of c, right? The average rate of change is the slope of that red line. The derivative representing the slopes of tangent lines you saw in calculus. Well, at the numbers c1 and c2, you can see that the tangent slopes, which I've drawn in kind of a dotted line there, I'll highlight the one at c1, it's parallel to that secant slope, that chord, if you like. There's another one down here. The tangent line at c2 is parallel. So the mean value theorem is saying that always has to happen. Maybe you should stop the video actually right now and just draw a few functions. Draw some functions on a closed interval. Just make sure they're continuous and differentiable. And you'll see that no matter how you draw them, there has to be at least one tangent line between A and B whose slope is equal to that secant slope. Cool. Okay, well, we're going to prove this by basically just sort of taking our function f, modifying it into a function that satisfies the hypothesis of Rolle's theorem, and then apply Rolle's theorem. So really Rolle's theorem is a special case of the mean value theorem, but you can get this general case from that special case, right? Because in Rolle's theorem, f of b and f of a are equal, so this average slope is zero in Rolle's theorem. All right, well, if it's not zero, we'll just subtract off something from f to make it zero. So here we go. So once again, I'm going to kind of borrow the notation. This is a busy slide. We'll work through it, but I'm going to borrow the notation from the theorem so I don't have to repeat it all inside of the body of the proof. So using that notation above, I'm going to start by defining a linear function L. And just what am I going to do? I'm going to make it have slope equal to that secant slope. Okay, so the slope of this linear function is f of b minus f of a over b minus a. And then I'm just putting it so that it goes through the point a comma of f of a. So you can kind of recognize the formula for this L of x. This is the slope times the change in x plus the y coordinates, the point slope form of a line. That's a linear function and hence differentiable. We proved that every linear function on the real line is differentiable. Differentiable functions are continuous. That's true actually for all x in R. So in particular for the x's between a and b. So L is differentiable in particular. I'm just going to write it down here on the interval from a to b. It's differentiable on the whole real line. It's continuous on the closed interval. It's continuous on the whole real line. Okay, cool. So then what do I do with that differentiable function? Well, I'm going to define a new function g by just subtracting L from f. So I'm going to scroll up here a little bit because I've sort of got a picture that you can see how I'm doing that. The picture is not super big, but remember f here, it's drawn in black. And what I'm doing is just y coordinate by y coordinate. I'm subtracting the y coordinates on that line L from the y coordinates on the graph f to make that blue graph g. All right. So I'm going to get to this in the body of the proof here, but you can see because f and L have the same y coordinate at a and b, well, g is going to be 0 there. Okay. I can just kind of walk you through the proof looking at this picture. G is the difference between two functions that are continuous. So it's continuous on the interval. Each one of these functions is differentiable on the open interval. So the difference is differentiable on the open interval. So long story short, G satisfies the hypothesis of Rolle's theorem. So that's all I've written here is that G is continuous on the closed interval. The exact theorem, difference of continuous functions is continuous, is 540. It's differentiable on the open interval. 7.7 says the difference of differentiable functions is differentiable. Okay, and then here I'm just calculating what's clear in the picture here. If you evaluate, you can stop the video and do the arithmetic yourself, but evaluating G at A, well, by definition, it's L of A, or sorry, F of A minus L of A. But let me scroll back so we can see our formula for L here. If you plug in X equals A, well, then this term is 0, so you just get F of A. F of A minus F of A is 0. All right. Likewise, G of B, plug the B's into F and L. Well, when you plug in B for this X up here, B minus A times 1 over it is 1. So you just get F of B minus F of A plus F of A. So that's what I've written here. Check out the arithmetic. That also is 0. It's clear in the picture, right? If G is just F minus L and F and L cross at A and B, then G is 0 at A and B. So what have we got for G? We've got a continuous on the closed interval, differentiable on the open interval. Its value at the endpoints are the same. They're both 0. G satisfies Rolle's theorem hypothesis. So Rolle's theorem says there's some point in between A and B that makes G's derivative 0. But again, by the same differentiation rule, 7.7, the derivative of G is the difference of the derivative of F and L. But by what we proved about linear functions, the derivative of L is just its slope. It's that number, f of b minus f of a over b minus a. So the derivative of g is just f prime minus that number. Well, so if g prime of c is 0, that means when you plug c into the right-hand side of that formula, you get 0, but that's just f prime of c minus that number. A little bit of algebraic manipulation. There you go. That's how you prove the mean value theorem from Rolle's theorem. Cool. We don't need to do this, but when I was making this video, I kind of got interested in sort of making this little cartoon. So this is a GIF animation of sort of slowly transforming the function f into the function g. So what I'm doing is I'm just kind of subtracting that line L, but in this animation, I've got this parameter t. You can see it at the top of the screen. And t is just going from 0 to 1. So when t is equal to 0, I'm not subtracting anything from f right there in the animation. When t gets to 1, I've subtracted L from f. So I get the function g. And I kind of like this animation because it shows you that the values that satisfy the mean value theorem, the C1, I don't think I can highlight on the animation. Maybe, oh yeah, I can. The values of C1 and C2, they don't change. Yeah, so those places where the tangent lines to the graph of f are parallel to that red chord, as you subtract off this linear function, they don't change. And so when you get to t equals 1, you get the same two c values from Rolle's theorem. Anyway, I liked watching this little animation, but it doesn't really add much to the proof. Okay, so we're going to end this video with a couple of corollaries. It's supposed to say corollary 1. And these are going to be kind of big deals for us when we study integrals, and you've studied integrals in calculus, so you've already seen these. We know from differentiation that the derivative of a constant is 0, and the first corollary says that, well, that's the only kind of function whose derivative can be identically 0, at least functions on intervals. So the preamble: if you take a function defined on an interval, suppose it's differentiable on that interval, so it has a derivative everywhere. If that derivative is identically 0, then that function is constant. Okay, so we know that the derivative of a constant function is 0 from our earlier work. This is saying that the converse is true. For functions that are defined on intervals, if their derivative is identically 0, then they're a constant. So how to prove it? Well, let's suppose that you have some differentiable function. I'm going to prove this kind of by contrapositive, but suppose it's not constant. Well, if it's not constant, there's a couple of points. Let's suppose that one of them is less than the other, and the outputs aren't the same. That's literally what it means to not be a constant function, is that you must have at least two different outputs. So let's call them f of a and f of b, and suppose that a is less than b. Okay, but we have a differentiable function. It's differentiable on I, so it's differentiable on the closed interval between a and b. Differentiable functions are continuous, so it's going to be continuous on that interval and differentiable on the open interval. So in other words, it satisfies the mean value theorem on that interval from a to b. Okay, so if you're kind of visualizing this, I is some interval. I don't know what interval it is, but there has to be this a and this b, and I'm supposing that the function values are different in it. And I know that my function is continuous on the interval from a to b, and it's differentiable on the open interval from a to b. So I can apply the mean value theorem. The mean value theorem says there has to be some number c somewhere between a and b. Maybe there's a bunch of them, but there has to be at least one of them that makes the derivative of this function equal to that average rate of change, that f of b minus f of a over b minus a. But we're supposing that f of a and f of b aren't the same. So the numerator of that fraction isn't 0, so the fraction's not 0. Okay, so what did we prove? We proved that if f isn't constant, under the assumption that it's differentiable on I, then its derivative cannot be identically 0. So by contrapositive, if the derivative is identically 0, then the function must be a constant. Nice. One more corollary before I quit this video, but I'm going to leave the proof to you. If you take two differentiable functions on an interval I, and suppose that their derivatives are identically the same. So that's a horrible phrase. Their derivatives are identical. So I've got two functions, f and g. They're both differentiable on I, and their derivatives are identical. That is, f prime of x is g prime of x for every single x in I. Okay, well, then there must be some real number, c, so that f is equal to g plus c. In calculus language, f and g might be called antiderivatives of f prime and g prime, and this is saying that the two antiderivatives differ by a constant. Okay, so that the equation holds for all x and I. So I'm going to leave that as a proof, an exercise for you. Okay, thanks for listening.